Hi students. In this lecture, I am going to discuss problems from Irodov. Let us see first one. A small body A is fixed to the inside of a thin rigid hoop of radius Kepler and mass equal to that of the body A. It is given. Hoop means ring. A ring and this small body, both having same masses. The hoop rotates without slipping over a horizontal plane at the moments when the body A gets into the lower position. The center of the hoop moves with a velocity v naught. See meaning of this. Whenever see since the ring is rolling, this body goes like this along with the ring. So whenever A comes to lowest position, velocity of center of the ring is v naught. See here, at the moments when the body A gets into the lower position, the center of the hoop moves with velocity v naught. At what values of v naught will the hoop move without bouncing? See meaning of without bouncing. It is without losing contact with the ground. Ring is not losing contact with the ground. So for what values of v naught? Right? Let us see how to start. Right. First make the given diagram. So it is a ring which rolls without slipping, and that small body, when it is at the bottommost point, velocity of the ring, it is v naught. So first we have to focus why ring loses contact with the ground. See how many forces that are acting on the ring. Its weight mg always downwards. Normal reaction from ground, it is upwards on the ring. So now there must be a force. There must be a force on the ring that must be upwards. If you observe carefully, when the small body reaches topmost point, so I'm making diagram here separately. Right, see carefully. When the small body reaches topmost point, forces that are acting on the small body. On the small body. You can see by the ring on the small body, force will be downwards. I am saying by the ring on the small body, force will be downwards. That is called as N. And next you can see weight of that body is also downwards. Now, by the ring on the small body, force is downwards. Then, by the small body on the ring, force will be upwards. According to Newton's third law, force by the small body on the ring will be same value. Direction is upwards. Okay. Now, if this force is greater than weight of the ring, then ring will lose contact. So first condition, N should be greater than or equal to mg. Or not to lose contact, N should be less than or equal to weight of the ring. So focus this condition carefully. So here what I am saying is, when the small body reaches topmost position, force by the ring on the body is downwards. Then by this body on the ring, it will be upwards. If this force is greater than weight of the ring, then ring will lose contact with the ground. Now question is without bouncing. That means a ring should not lose contact with the ground. That happens if force by the small body on the ring is less than or equal to mg. Equal to means just losing contact. Less than not losing contact. Okay. Now focus how to get the value of n. Okay. So here if you observe with respect to center of the ring, with respect to center of the ring, this body follows now subtler path. It is now rolling. Rotation is now clockwise. Now see carefully here. I am saying with respect to center of the ring, this body follows subtler path. Now we have to focus who is providing centripetal force. So one is by the ring on the body, force is downwards. Its weight also downwards. So both are now towards the center of the ring. That means centripetal force is N plus weight of the body. This is now centripetal force on the body. That is equal to mass into centripetal acceleration V square by R. So I have taken force equation for the small body. Okay. Next. Now in this we require n value. Right? If we know n value, then we can take n value here. Then we get condition. Now to get n value, we require v value. So what is v? It is velocity of the ring, or we can say speed of the ring, or speed of center of the ring when small body reaches topmost position. So here v naught when smaller body is at the bottommost position. V is now speed of the center of the ring when smaller body reaches top position. Now here it rolls without slipping. So we can take conservation of mechanical energy. So by using that, we can get V value. Let us see. So I'm taking here conservation of mechanical energy. So kinetic energy equal to half m V naught square into 1 plus beta because it is rolling without slipping. This is now kinetic energy for the ring. Okay, only for ring. Next, when this is at the bottommost point, for bottommost point velocity is zero because rolling without slipping. That means it has no kinetic energy for the smaller body. Okay, and if we consider ground as reference level, it has no gravitational potential energy. Okay. Next, coming to for the ring, I am not taking gravitational potential energy because center of the ring is always at same height. Even if you are taking that, that will cancel on both sides. I am repeating. Here I am not taking gravitational potential energy for the ring. For the ring, how much we have to take? mg into r. And center of the ring is always at same height. So no change in the gravitational potential energy of the ring. That's why I'm not taking that. Now this is equal to when it reaches topmost position for the ring half m b square into 1 plus beta. Beta value is 1 for ring. This is a kinetic energy for the ring. Okay. Coming to for the small body. If center of mass velocity is v, for topmost point velocity is 2v, right? It is now half m, speed is 2v. So 2b whole square. That is the kinetic energy. Next, we have taken ground as reference level. Now it is at a height of 2r. So potential energy for the small body, that is mg into plus mg into 2r, right? Now simplify this. We want to get n value. So we require mv square or mv square by r value how much? Okay. So here what we can do, 2 and 2 gets cancelled. 2 and 2 gets cancelled. 2 and 2 gets cancelled. mv naught square. And I want mv square by r. Do one thing, mv square. Okay. This is 2 square 4. 4 by 2 remaining is 2. 2 plus 1, it is a 3. Okay. So 3mv square is equal to, let me cross check once, mv square. This is a 4 by 2. It is a 2. So 3mv square, that is equal to, here what is left? mv naught square, right? mv naught square minus 2mgr. Okay. So we want mv square by r. I will do one thing here. I will calculate directly first of all mv square. mv square equal to mv naught square by 3 minus 2mgr by 3. Okay. Next. And we want mv square by r. So I'm dividing both sides with r. With r. So r. So here r. And here r. Okay. R cancel. Right. Now see what is n value. N equal to mv square by r minus mg. That means mv naught square by 3r minus, this is how much? 2mg by 3. 2mg by 3 minus mg. See carefully. This is mv square by r. In the place of mv square by r, take this value minus mg. So minus mg. Right. So this value how much? 2 by 3 and this is 1. 1 plus 2 by 3. 5 by 3, right? So it is now mv naught square by 3r minus 5 by 3 mg. Cross check once. 2 by 3 plus 1. 5 by 3. Now this is a value of n. Okay. This n value should be less than or equal to mg. Okay. Now see what we get. mv naught square by 3r should be less than or equal to, I'm taking this one to right side, 1 plus 5 by 3. 1 plus 5 by 3. 8 by 3. Okay. 8 by 3 mg. M gets cancelled. 3 gets cancelled. V naught should be less than or equal to root 8 to gr. Okay. That means V naught value can be maximum root 8gr. Maximum. Okay. Means for any value that is less than root 8gr, ring does not lose contact. For any value of V naught that is less than root 8gr. If it is equal to root 8gr, just loses contact. Okay. So I hope you got a clarity. Main thing we have to focus, why ring is losing contact with the ground. If you get that idea, writing force equation, then writing conservation of mechanical energy and remain just calculation part. So I hope you got a clarity. Let us go for next problem. Right, see the question given. A man of mass m1 stands on the edge of a horizontal uniform disk of mass m2 and radius r, which is capable of rotating freely about a stationary vertical axis passing through its center. At a certain moment, the man starts moving along the edge of the disk. He shifts over an angle phi dash relative to the disk and then stops. Okay. So given disk, uniform disk, stationary, a man starts moving on the edge of the disk. In the process of motion, the velocity of the man varies with the time as v dash of t. Assuming the dimensions of the man to be negligible, find the angle through which the disk had turned by the moment the man stopped. The force moment relative to the rotation axis. The force moment, its meaning is a torque. Okay, moment of force relative to the rotation axis with which the man acted on the disk in the process of motion. Okay, let us see how to start. Right, now see condition. It is a uniform disk given freely rotating about a stationary vertical axis. Imagine this board is now horizontal plane, okay, and we are seeing from the top. That means axis will be towards us, okay. So disk is now in a horizontal plane. Disk is in horizontal plane. This is now axis, which is now towards us, or we can say normal to plane of this board. So we are taking board to plane as horizontal plane, okay. Next, a disk radius is r and its a mass. Man mass m1. So man mass m1 and disk mass is m2. Okay. Now you can see there is a person here walking on the edge of the disk. Now you can see the man starts moving along the edge of the disk. He shifts over an angle phi dash relative to the disk and then stops. For example, initially at one instant, the person was at this position. Let us say the man walks anti-clockwise, means we are seeing from the top. Man walks anti-clockwise. See given over an angle phi dash relative to the disk. Okay. So now he is walking anti-clockwise through some angle. So this angle is now phi dash. That is now relative to the disk. So when he walks anti-clockwise, the disk rotates clockwise. Okay. Suppose that is now theta. So which we have to calculate. Okay. Now see what we can do. About this axis of rotation, we can consider angular moment. That means initially person was at rest. Disk also, it was at rest. So initially, angular momentum for the system means man and disk, it was zero. So it is always zero. Okay. Then see what we can write. Net torque zero means net torque. Net torque is equal to rate of change of angular momentum with respect to time. This is zero. That means L bar is a constant. L bar is a constant. Okay. Initially, disk was at rest, man was at rest. So angular momentum zero. So now also it must be zero only because net torque equal to zero. Right? Then see what I can write. See here I can write I1 omega 1 bar plus I2 omega 2 bar equal to 0 bar. So angular momentum of the person plus angular momentum of the disk total equal to 0. Okay. That means I1 omega 1. For example, 1 stands for person. This I can write as d theta 1 by dt. That is equal to minus I2 d theta 2 by dt. Okay. See, this we can compare with. So while learning, center of mass, while taking conservation of momentum, if you remember, a man standing on a stationary plank. So plank was on a smooth surface. Initially, person was at rest. Okay. Initially, person was at rest. Plank was at rest, and plank was kept on a smooth surface. Now, person starts walking. Let us say plank length is initially he was at one end. Now he reaches other end and comes to rest. Now find out distance moved by the plank. Okay. If you remember, there we have taken like VCM 0. Okay. So we have taken delta XCM equal to 0. That implies M1 delta X1 plus M2 delta X2 equal to 0. Exactly same kind of logic here. I1 omega 1 means I1 delta theta 1, I1 delta theta 1 plus I2 delta theta 2 equal to 0. See here what happens. If you take integration on both sides, then we are going to get I1 delta theta 1 is equal to minus I2 delta theta 2. See once here, M1 delta X1 is equal to minus M2 delta X2. Same kind of equation. Okay. Right. Now see carefully. I1. I1 is for the person. For the person about this axis. Moment of inertia is, it is M1 R square. Right? Just like a point mass. Delta theta 1. With respect to disk, he moves by phi dash, but now disk rotates clockwise. In ground frame, he moves by phi dash minus theta. If you take anti-clockwise as opposed to, this is a completely our choice. Okay. That means phi dash will be positive anti-clockwise. Theta will be negative because clockwise. So in ground frame, his angular displacement is phi dash minus theta. Okay, that is equal to for the disk. It is m2 r square by 2 into rotation is now clockwise. That's why it is minus theta, right? R square gets cancelled. Now solve for theta. Then see what we get. Solving for theta, this is minus of minus plus. Having here minus, I am taking this m1 into minus theta right side. Then see what we get. Theta into m1 plus m2 by 2 is okay. Theta into m1 plus m2 by 2. That is equal to m1 into phi dash. So just calculation part, nothing else. So theta equal to, it is a 2m1 phi dash upon it is a 2m1 plus m2. Remember here we have taken sign convention. So we got here only value. And if you see in the solution, they have given negative sign, okay? The reason is that phi dash is anti-clockwise and theta is now clockwise. If you want the sign, then take it as negative here. So while negative, phi dash is anti-clockwise. Theta is clockwise. That's why negative here. Okay, right. See next what we have to calculate. Next, in the process of motion, the velocity of the man varies with time as v dash t. So we have to find here the force movement relative to rotation axis with which the man acted on the disk in the process of motion. That means we have to find torque. Torque on what? Torque on the disk. Okay. So torque on the disk means first of all we have to focus what is alpha of the disk. Okay. So to find that, so we got here angular displacement of the disk. We got here angular displacement of the disk. We want to calculate angular acceleration of the disk. Okay. Then we can take into y. That gives us a torque of the disk. Differentiate this now once. Then see what we get. D theta by dt. This is giving us omega of the disk minus 2m1 upon 2m1 plus m2 into d phi dash upon dt. And remember, this is nothing but omega of the person, right? And omega means it is v by r. In the place of this, what I'm writing here, minus 2m1 upon 2m1 plus m2. This is omega dash, means corresponding to the person. That can be taken as v dash by r. So v dash of t. So I hope you are getting this point. This is omega of the person. Omega equal to v by r. So v dash of t by r. Now differentiate once again. We get alpha of the disk minus 2 m1 by 2 m1 plus m2. This remains same. Now derivative of this. So 1 by r d by dt of v dash of t. This is alpha. Now to find torque, the torque equal to I into alpha. Now take this alpha value in this one. Then we get torque acting on the disk. So here I value how much means? It is m2 r square by 2 for the disk. That means first we got angular displacement of the disk. Differentiate that. angular velocity of the disk. Differentiate once again. We get angular acceleration of the disk into I. That gives torque acting on the disk. Okay. So I hope you got that clarity.